So I move on to the next section on 6.8. That's streaming. Streaming compared to voice over IP, it is sub real time. Sub in the sense that because it's directional, one way. It's only one way traffic. Voice over IP is two-way real time, but here it's a one-way real time. So the traffic run mostly from the server to the client. So not much traffic from the client to the server. So it's sub real time. It means that I can defer the real time streaming data by 1 second or 2 seconds or 3 seconds without degrading the perceived quality of the user. So I can defer 2 seconds. The start time of the video playing can be deferred by 2 seconds, and the user is still happy as long as the playout is smooth. The playout is smooth means that I don't need to when I'm viewing the video, when the client is viewing the video, once it stops playing, it would not stop to wait for. Once it started, it would not stop to wait for the video traffic to come in order to play. Okay. So usually, in order to do that, you usually put a jitter buffer to preload the multimedia traffic into the jitter buffer, say for 2 seconds or 3 seconds, and then you start to play. Okay. And of course, another comparison, we compare streaming with voice over IP. We also like to compare streaming with stored video or video download. It's different. Where stored video or video download means that in order to view a video, you download first, and then you play. That means if the video is 2 gigabytes, then you need to spend time to download the video. And once the entire video has been downloaded to the client, then the client starts to play. And if that would take 2 minutes to download, then you wait for 2 minutes. But for streaming, you don't wait that long. You probably wait for a few seconds, say 2 seconds or 5 seconds, so that your jitter buffer has been preloaded with video data, and then you start to play. You don't want to wait until the entire file has been downloaded. You just wait for the preloading for the first few seconds of video to be downloaded, and then you play. And while you are playing the video, the download is still continue. Okay, so the waiting time, the initial waiting time of streaming, is much smaller compared to the stored video or the downloaded video. Okay, so you can start earlier. You don't want to wait for 2 minutes before you can view the video. You want to wait for only 2 seconds, and then you want to see the video. And while you are viewing, the download continues. And it's a it's a short fetching time. The fetching time is short, and the storage requirement is low because you don't need to store the entire video, say 2 hours of video. No, you don't. You just keep a small, probably you only keep tens of seconds of video in the buffer. And it's also suitable for live broadcasting. If it's live, then I don't know whether you have tried to use the internet, IPTV, and radio, internet radio. Then you can do an experiment by watching the video, the live broadcasting video, and all the live radio, and while have a traditional TV or traditional radio besides you, and you turn both on to the same channel and see whether they have different latencies. And yes, it is. You will find that if you do IPTV or radio, internet radio, that usually the play-out time is several seconds slower than the traditional TV or traditional radio. Do you know what I'm saying? Because of what? Because they put some jitter buffer. Because on the internet TV or internet radio, they put some jitter buffers, usually several seconds, in order to preload. So every video, every piece of video and audio has been delayed by 2 seconds or 3 seconds, compared to the analog or traditional way of broadcasting, or digital broadcasting, or compared to the broadcasting not going through the internet. Okay. So you still have good quality of live broadcasting, except that it has a delay of several seconds because of the jitter buffer, mostly because of the jitter buffer. And you would do compression for the streaming. You would also do compression, and and it has a protocol stack for streaming, and also the QoS and synchronization mechanism. Okay, here is the architecture for streaming, where on the right-hand side you see the client, left-hand side is the server, and the server has either stored video on video audio file, or live. They could be live from the real-time input, and then they could do a QoS control to encode the video or audio into, say, layers, into different layers, usually into different layers, so that you would drop the the QoS control here could be a layered encoding, where the base layer is more important than the first layer. The first layer is more important than the second layer. And the other thing it can do is in doing the encoding of video and audio, they could put some redundancy, so that if some packet has been dropped, the audio or video could be still reconstructed, even some piece has been dropped. So that's done in the encoding with layered encoding and also redundancy encoding, and then transport protocol onto the internet. And then on the client, it would do retrieve from the transport protocol, and then some QoS control to handle the layer coding and redundancy coding, and then put it into the decoder, video and audio decoder. And the video and audio decoder need to synchronize. Usually the video stream is synchronized through the audio stream, so that they are played back at the right time, according to their timestamp. For example, if I don't do this kind of synchronization, then the video and audio would not be synchronized. The play-out time would not be this. I mean, if the timestamp, if I'm playing the video, I want the audio to be played. The audio with the same timestamp should be played at the same time. The audio data with the same timestamp as the video should be played out at the same time. Okay, that's synchronization. And when talking about encoding the audio-video data, you usually need to do compression. Otherwise, the bit rate will be too high. So there are a number of compression schemes. Either they would describe the changes between frames, or describe the similar pattern in the frame. Okay, either the changes or the common part. Okay, and the compression could be either lossless or lossy. Lossless means that it's almost fully recoverable by the decoder. And two examples are the GIF is a lossless encoding, while JPEG is lossy encoding. So when you have lossy encoding, it means that the decoder cannot fully recover the data. Some of them will be lost, which is fine as long as the loss is not serious. And it could be the encoding or compression could be symmetric or asymmetric. By symmetric, it means that the time spent for compression is the same as the time for decompression. Okay. However, most coding are asymmetric, which means that usually it means that it takes longer time to compress, but less time to decompress. So here's the protocol stack that for streaming, you have the RTP for the data plane, RTCP for path quality reporting, and then RTSP for real-time streaming protocol. And this is a protocol for streaming control. It's more like a VCR control function, VCR style remote control function that you could pause backward, fast forward, fast backward, all these kind of functions. So it's very similar to VCR control, the RTSP. Okay. And the RTSP message is also similar to HTTP protocol messages. Okay. However, there are some streaming application that write on top of HTTP directly. For example, YouTube. YouTube write on top of HTTP and does not use RTSP and UDP. Instead it write on top of HTTP and TCP. So if you write on top of HTTP directly, then the audio data has been carried by TCP instead of UDP. If you write on top of this, your audio data might be carried by UDP and might be carried by TCP. That depends on some of the applications allow the user to change the default. Okay, you could configure that. For example, the real player and the media player, they allow user to configure whether you want to run on TCP or UDP. What's the advantage of running on TCP? And the disadvantage. The advantage is that because TCP had retransmission, so the quality is likely to be better because it has retransmission. But the disadvantage is that the TCP will do flow control and congestion control. So if your real-time stream suffer congestion, you will be flow controlled, and you will find that the playout is not smooth. Even the playout will be delayed, but the audio video quality is good, but the playout will be delayed. So that will introduce jitter to the users. The user will see the video or the audio is having jitter, even though each piece of the audio video has been there, because TCP provide reliability. But if you run on UDP, the advantage is that you won't be flow control or congestion controlled. You can send whatever you want. Okay, it depends on the codec to adjust. If your codec is adaptive codec, then it would adjust according to the network condition. Okay, and you would not be flow control, congestion controlled. And so the chance of having jitter is less when the network condition is a little bit worse. When the network condition is a little bit worse, then you would drop some packets. The UDP packet will be, some of the UDP packet will be dropped. However, the playback will be smooth, but the quality will be degraded. So it's like, consider this. If you run on TCP, so for example, YouTube run on TCP, every piece of audio video has been there because it will be retransmitted. But when the network condition is bad, then you would have jitter. The playout will have jitter. The audio will have jitter. Okay. However, if it's a real player or media player running UDP, then the playout will be smooth, but the quality is degraded. For example, the video quality is degraded. It's still smooth, but degraded. Okay. Then it depends on which way you like. Some people want, I don't care the quality is degraded as long as it's smooth. I don't like jitter, because jitter, it means that I have to wait. Okay. Okay, and the QoS and synchronization mechanism, where the QoS would do probably do a rate control, which would adjust the rate of the codec. You would, depending on the network condition, you could adjust the codec rate. If the network condition is bad and the codec rate is still high, then a lot of packet will be dropped. So when the network condition is bad, then you want to reduce the bit rate. Okay, and the synchronization is about we talk about the audio video synchronization, that mostly it's a video playback to be synchronized with the audio playback. So the timestamp of the video data and audio data you play should be the same. You can't say I'm playing a 2.5 second of audio while I'm playing a 2.1 second of video. No, it would be a problem. So they need to be synchronized, and that's called interstream synchronization. So interstream synchronization. And there are also intrastream synchronization, which is about the continuity or smoothness of the data. So you don't want your video, when you're playing the video or audio, you want the playout to be smooth, non-interrupted. So the playback, so you want the continuity of the stream. So if I play say 30 frames per second, I have played 30 frames this second. I want to play 30 frames in the next second. If I can only play 20 frames in the next second, and while the other 10 frames in the next second, then it's not smooth. It's not smooth. The continuity is not good. So that's a intra-frame synchronization. And there's also inter-object synchronization. It's a synchronization with the other objects, not stream but object. For example, the text and still image. For example, so in a TV program, you have one video stream, two audio stream, and also one text stream, right? Text object on the bottom of the screen, and the text message should be synchronized too. You can't say okay, unsynchronized, then it'll be a problem. The speaking, the speaking, the text, the video all need to be synchronized. That's inter-object synchronization. And those synchronizations should be done at by the player when it's played back. Okay, the open source implementation, which is Darwin. Darwin is the server of QuickTime. You know QuickTime? The QuickTime is the media player. I mean the player of streaming player by Apple, and Darwin is the server. So the client is called QuickTime. The server is called Darwin, and it was competing with real networks, real player, and also Microsoft media player. Okay, so however, as Microsoft and real media taking the lead in the market share, Apple is losing the market share. So they decided to open source QuickTime and Darwin, so that they would. So essentially it's not a business that earn money. So Apple decided to open source, so that more people can get involved to maintain it, and less resource can be devoted inside the Apple. So that's the background of Darwin. And of course, it delivered the media, streaming media by RTP and RTSP, real-time streaming protocol, and provide live and on-demand, either live or stored video, and support many formats, and has a web-based administration interface. And one feature, I mean, the Darwin server also need to achieve concurrency. So the way it achieves concurrency is by text thread. Unlike Apache server, which achieve concurrency by thread per user, thread per client, here they don't associate thread per client. They don't associate a thread to each client. Instead, a client will be handled during the entire service time will be handled by multiple threads. Okay, I recall the term. It's called worker thread. The worker thread model. The worker thread model is different from the per client thread. In the per client thread model, you only associate a client. You dedicate a client. You dedicate a thread to each client. So for the entire service time of a client, it will be served by just one thread or just one process. Okay, but here you don't want the worker thread model says that each thread would do a specific task, and there'll be a group of threads handling a specific task, and a client being served by a server will be served by a sequence of threads, okay, by multiple threads. So in this case, when the client it will be served by a specific thread, and then the thread would execute some module here, and then once a module has been finished, then it will put the thread into a queue, and then waiting for another thread to serve the client. So here it represents a task, a circuit event, and once it is served, then it would join the queue, and the worker thread will serve the queue. So if there are so there's a queue for each task. This is complicated. Okay, so there's a queue for each task. For example, that a client would join the queue, and then the thread would then each thread will work as a server that would take one client from the task queue and serve the client. And once done, it will be the client will be put into another queue. Okay. So if a client needs to be served by three tasks, then over the service time it will join three queues. So it joined the first queue and waiting to get served by a task. Waiting to get served by a thread. And once it finished the service by this thread, it will be put into the second queue, another queue, and waiting to be served by another thread. And for each queue, each task queue, there will be multiple threads serving the queue. Okay. So if I have multiple threads, I would allocate some threads serving this queue, some threads serving the other queue, some threads serving the third queue. Okay, so this is how the worker thread model works. With this kind of worker thread model, the scalability is higher in terms of the number of clients you can serve. I remember I discussed this. If it's a per client thread or per client process, then if you have 1,000 clients, then you need 1,000 processes or 1,000 threads to serve all these 1,000 clients. What if you have more than 1,000? You have 5,000 clients being served. Then you would need 5,000 processes or 5,000 threads. That will be too much. Okay, so with worker thread model, you could serve 5,000 clients with just a limited number of threads. Say I allocate 50 threads serving this task queue, the other 50 serving this task queue. Okay, then they could serve a quite large number of clients, while still achieving good concurrency.